Okay, so here's problem one on the 2020 6-week exam that's on the course website for practice. So this one is, given the following assembly code, show any updates to the registers in memory, cross out the old bytes of memory if it has been overwritten. So similar to the quiz we had, we're looking to see what happens when we do moves and loads and stores. So the first couple, just reading straight down the code, we're going to start with a move W into R0 of CO20. We're going to be smart about this and see that the next instruction is a move T, R0 2009. So we know that move W affects the bottom 16 bits, and that's going to be C020 into R0. Our destination is R0 here. And then the front part is going to be 2009, because that's what move T does, is it puts something in the top 16 bits, and combined they can establish a single 32-bit value in a register. So that's R0. R1 is going to be similar, right? It's a move W and then a move T. So OX 2009 CO40. So we're just copying from the instructions those values into a register. So keep in mind, moves affect registers. That's what we're doing here. The next set of instructions we can see is the common trick, which is that we have a move T and then a move W. And we should have a move W and then a move T, because move W wipes out the top 16 bits when it does its move. So we're going to move COO into R2, but then we're actually going to cross that out. So we would have C000 and then whatever had been there before in R2. But we're going to cross that out because that gets erased by the next instruction, and we're going to end up with 000000000 across. And that's because that move W R2 wipes out the top 16 bits, and it sets the bottom 16 bits to zeros. So we don't actually have anything left in there because we've wiped out all of the stuff that had been there before. So that's it for the moves. Now we go on to the load and store instructions here. So the first one is load R3, R1. So keeping in mind here, a load, the register that we give outside of brackets is the destination. So that's the register that we're going to put the result into. Remember, load is getting something from the memory, so from the address space up here, and putting it into registers. Stores are going the opposite direction, where we're taking something from register, putting it into memory. So here, we're going to take something from the address R1 that's stored in this register. So we're going to take whatever is currently at 2009 CO40. We're going to find that address in memory, and we're going to put that into register 3. So let's find that in the memory. So 2009 CO40 is our address R1. We'll find that here, and it's a load, an LDR, so it's getting the full 4 bytes. Each box here is a byte, and so we're getting 4 bytes of memory, or 32 bits of memory. Keeping in mind that in memory this is stored in little endian order, so the smallest byte is first, or the lowest order byte is first, and then they go in increasing order. So when we write this out in R3, we're going to say FF, that's the rightmost byte, FF, next rightmost byte, 0, 0, and then finally the lowest order byte, the 1, 1. So that's what goes into that register for that load. Next up, we have a store from R3 into R0. So stores go the other direction. The register outside of brackets is where we're getting the value from. The thing in brackets is where we're taking it to in memory. And so we look at R0, we see that that's 2009 CO20, and we're storing the value from R3. So we're just going to take that value that was at this memory location. Now it's in the register, and we're now going to put it into this other memory location at CO20. So that's these 4 bytes here. That's the store. And we're going to be able to just replicate what was in memory. So it was in little endian order here. It's going to be a little endian order there. So we're going to cross these out because we're going to replace it with 11, 0, 0, FF, FF. I know we're replacing 0 with 0 in that second byte, but we can cross it out because we are overwriting it whenever we store that into memory. So that's the second store. Or that's the first store. We're changing memory there. The second store, we're taking the value from R2, and we're putting that into R0 plus 18. So that offset syntax means take the memory address in R0, add OX18 to it, and then we're storing the value from R2. So R2 is all zeros. we're going to store that into the memory address in R0. So R0 OX18 is actually going to expand to, we have what's in R0 now. That's OX2009 C020. And then we're going to add OX18 to that. We just do math like we would in decimal land. And in this case, we don't end up going into the hex digits anyways. So we end up with 2009 C038 in hex. And so that's the address we're looking for here. So we've got the closest thing on the left to it is 2009 C030. So that's that byte. It's 31, 32, 33, 34, 35, 36, 37, 38. A good idea is just to label these whenever you start the exam or start a problem like this, so that you have an easy reference for where these are in memory, and you can just label them in hex so that you can quickly look these up if we have a question that asks you to do that, which is fairly likely. So we can just label those off, and then we can find that the 8 is here. This is an STR, which means it is a full, again, 32-bit, which is 4 bytes store. So we're going to affect those bytes in memory, and the value we're storing is coming from R2, which is the all zeros value there. So we're just wiping all this out, putting zeros into that memory. Okay, the final instruction here, we have a load sh. The sh part of this stands for signed half word. So a half word is 16 bits, and the S means we're going to sign extend the value that we get from there. So we're going to look at the topmost bit of the half word that we load, and we're going to sign extend from that. So here again, we're looking at the address in R1, and we're adding 6. In this case, it's 6 in decimal, but same thing as 6 in hex in that case. So our address is going to be R1, OX2009, C040, plus 6, which is going to be the OX2009 C046, of course. So we're going to find that in memory. That's this set of bytes. And because it's a half word, we're taking 2 bytes instead of the LDRs that take 4. So we're getting EF01 out of memory. And again, we got to remember that this is in little endian order. So the EF is the sort of lowest order byte, and then the 01 is the higher order byte. So when we write this out, we would write that as 0x01EF, which means that the topmost bits are going to be 0000, and then if we wrote out the rest of it, we'd write out that in binary. But really, we only need to know what the topmost bit is, or the leftmost bit is, of the thing that we're loading. Since that is a 0, we're going to sign extend. That means we're going to add zeros. We're going to pad with zeros to the left of what we put in R4. So we're going to have 000001 EF. And keeping in mind that padding is to give us a value that we took 16 bits from memory, we have to decide what we're going to do to fill up the rest of the 32 bits. Every register is always the full 32 bits. So that's it for the first part of that problem. That's part A. The second part is the programmer who wrote the assembly code wanted to turn on only LEDs P1.31 and P1.29. What changes would need to be made to the code to accomplish their goal? So we have to understand the semantics of what this code is doing at that point. And hopefully, you could look this up, but you can also just, use the references we have from class to understand that this 2009 CO20 is actually FIO1DIR, right? OX 2009 C040 is actually FIO2DIR. And then the address that we stored to in this part of the problem, the OX2009 C038, is actually FIO1 set. So that is the way to turn on pins whenever we store that to that address in memory. And what we had stored into that address was actually all zeros. So the way we want to fix this code is we've set them to inputs. If we look at the values that we put into from R3 into FIO1 dir, we should see that the top 16 bits are all set to outputs. They're all ones, and then the bottom, I guess that's bits 0 and bits 4 are set to outputs as well from this value. That's what we put into FIO1 dir. That's what we have in FIO2 dir. And so those pins are outputs. That means if they're outputs and the value for set is 0, that means they're off. But we want them to be on instead. So to make them be on, we could change one small thing about this code, which is the move W, move T here. We're actually pretty close to what we would want to happen in the original instruction, but we need to swap that, and then we need to set the correct pin values. So to get the values for 31 and 29, we can write out what that looks like in bit order. 29, 28. So this is just going to be the leftmost hex digit is what we're going to see here. We want 31 to be on, we want 30 to be off, we want 29 to be on, and we want 28 to be off. And then we want the rest of the things to be zeros extended the rest of the way across because we don't want anything else to be on here according to the goal. So we're going to put A and then zeros into the rest of this. So OX A0000, that's what we want to have in R2. And that means that we need to have a move W of R2, 0, and then a move T into R0 of OX A000. And that should be it. So all we really need to do is make sure that we put that value into R0, into R2. I made a mistake there. So that should be a 2. We're putting into R2 the value A000, 0000, and that'll allow us to change bits 31 and 29 to on, and that's what we wanted the code to do for pins LEDs 131 and 129. So that's it for problem number 1.